Alright guys, now we're talking about these cardiac output variables separately. Now stroke volume is the volume ejected from the left ventricle in a single cardiac cycle. It is affected by what you put into the ventricle. This is our preload that we're talking about. How hard the ventricle squeezes the blood is also going to be a factor. This is contractility. And what the ventricle has to push out against is defined as the afterload. So all of these are going to determine our stroke volume. Now contractility increases in situations where we activate the sympathetic nervous system. And we're talking about anxiety and also when you get your pump on in the gym, such as exercise. This is due to an increase in the sympathetic nervous tone. Remember that. Now in pregnancy, it is a much different situation. The increase in plasma volume leads to an increase in preload. This stretches the sarcomeres so that there are more myosin binding sites that will be exposed for the next power stroke. Remember, actin-myosin interactions. Now, you will probably be asked about contractility a lot because of the physiology and pharmacology associated with beta blockers. So let's go ahead and go deeper into that. To understand the factors that determine contractility, we need to understand how myocytes work on a cellular level. So let's use an image and understand myocyte physiology, and then we can talk about how catecholamines and calcium change contractility. So you can see here we have our sarcolemmal membrane that has these deep invaginations, what we call T-tubules or transverse tubules. Within these T-tubules there are these L-type or long-acting calcium channels. They're incredibly important calcium-induced calcium release that is rather unique to myocytes. So these are voltage-gated L-type calcium channels. They're going to be stimulated to open by sodium channel depolarizations. So when they open, calcium is going to influx into the cell. So this new intracellular calcium is then going to bind to these ryanodine receptors and cause a conformational change in the RYR or ryanodine receptor, opening a route for calcium to fly out of the sarcoplasmic reticulum. So it's going to come pouring out of the SR, and this calcium is now going to be able to go and bind troponin C on our myofilaments. So we get the necessary conformational change in tropomyosin to expose the myosin binding sites of actin, so we get our contraction. This is a key point, so listen up. The amount of calcium within the myocyte is directly proportional to the contractility, so C for C. Because more calcium leads to more myosin-actin interactions, this is directly proportional to the contractile force. So what's this little PLB thing right here? And what is all this little ATP on the sarcoplasmic reticulum membrane? Well, the ATP symbol is for the sarcoendoplasmic reticulum calcium ATPase. We're going to use CIRCA so I don't pass out every time we say that. Now, what does CIRCA do? Well, it uses ATP to pump calcium from the cytosol, which is this area here, back inside the sarcoplasmic reticulum. So what's the PLB? Well, PLB is phospholamban. We can write this out real quick. Phospholamban. Phospholamban's job is to inhibit CIRCA from working properly. Phospholamban inhibits CIRCA from pumping calcium into the sarcoplasmic reticulum. This is crucial in understanding how sympathetic stimulation can increase contractility in myocytes. So if your phospholamban is working very hard, so we have an increase in PLB activity, it's going to decrease the amount of calcium that's going to be stored within the sarcoplasmic reticulum. So we limit the amount of stored calcium in the SR. So the next contraction, we're going to have less calcium available for future conformational changes in tropomyosin, and there'll be less interaction of myosin and actin. This means that we get a decrease in the force of contractility. Now, we've established all of this. We can use this to understand how beta-adrenergic stimulation or blockade or drugs such as digitalis can manipulate calcium concentrations to change contractile force. So how does the sympathetic nervous system increase contractility? Let's use this image to understand. So pick your catecholamine of your choice, epi or norepi. These are going to bind to these beta-adrenergic receptors on the sarcolemmal membranes of our myocytes. This leads to an increase in activity of the G-stimulatory protein associated with the intracellular part of the beta-adrenergic receptor. So this GH will ramp up adenylyl cyclase activity, which means that we get more cyclic AMP. More cyclic AMP liberates protein kinase A. It binds the regulatory domain of protein kinase A in order to set it free. Now protein kinase A is now going to be free to go and phosphorylate phospholamban. We can see that here. It's also here on this other side of the diagram. So protein kinase A will phosphorylate and inhibit phospholamban. So there's decreased PLB activity. Protein kinase A will also phosphorylate these L-type calcium channels to increase the influx of calcium. So this increase in calcium will be used to bind troponin C in our myofilaments and increase contractile force. Remember, we expose actin binding sites and the end result is a more forceful contraction. So I know that was intense, but the second messenger system and the sympathetic nervous system are super high yield. So I hope this integration gets stuck in your mind. Let's talk about this one more time. Beta-adrenergic activity leads to a decrease in phospholamban activity, so we can store more calcium within the sarcoplasmic reticulum for future contractions, and we also liberate protein kinase A to open more L-type calcium channels to increase calcium within the cytosol. Now, how does digitalis lead to increased contractility? Well, let's see that here. It competes with potassium at the extracellular binding site here on the sodium-potassium ATPase pump. Note how there are many pumps on the sarcolemmal membrane. This means that this pump will affect the others because it will not be able to pump enough sodium out of the intracellular environment. This eliminates the gradient for the other pump on the membrane, the sodium-calcium antiporter, which is NCX. Because we increase the intracellular sodium, there will no longer be a gradient to pump this in and pump calcium out. So where is this trapped calcium going to go? Well, our friend, the SERCA, or represented by the ATP on the sarcoplasmic reticulum membrane, is going to take it and put it in the sarcoplasmic reticulum for future contractions. So now let's discuss some ways to decrease contractility. So what are some ways we can decrease contractility? Well, heart failure in the situation of systolic dysfunction means that the ability of sarcomeres and these myofilaments here to expand and shorten has been lost due to overstretching. We're not going to be able to properly create the crosslinks required for a contraction. Now, in the situation of acidosis, which is low pH or high hydrogen ion concentration, will also cause decreased contractility. Now, this is a tricky one. So what happens is that these protons will compete with calcium at the L-type calcium channels. So there's competition for the influx of calcium. In the situation of hypoxia, which is low oxygen, and hypercapnia, which is high carbon dioxide, we're going to decrease cell respiration, and this means that the production of ATP will also decrease. Now remember that hydrolysis of an ATP molecule is necessary to take the myosin head back into the COX position so that it can be prepared for another contraction. In addition, non-dihydropyridine, which are verapamil and diltiazem, directly compete with calcium at these L-type calcium channels in the heart. So we said that we could increase contractility with beta-adrenergic stimulation. So again, now let's look at this image. Would it make sense that beta-adrenergic blockade would lead to a decrease in contractility? And that's yes. Of course, beta blockers antagonize these beta-adrenergic receptors. This leads to a decrease in the amount of cyclic AMP available. With less cyclic AMP, we do not liberate protein kinase A, and there's going to be an increase in the activity of phospholamban, which means that there's going to be a decrease in the amount of calcium available to be stored inside the sarcoplasmic reticulum, and there's also going to be less phosphorylation and opening of these L-type calcium channels. Important to notice here is that there's also a muscarinic M2 receptor. This receptor also uses the exact same second messenger system. Notice how instead of a GS, there's going to be a G inhibitory protein. This limits adenylyl cyclase activity, so there's going to be a decrease in the amount of cyclic AMP available. Notice this little negative sign here, inhibiting adenylyl cyclase from doing its job of converting ATP to cyclic AMP. Now we're going to see this diagram again in the pharmacology section. Let's shift gears now to myocardial oxygen demand. When you think about myocardial oxygen demand and use, equate it to the generation of ATP. So myocardial oxygen demand equals ATP in your brain. This is because we need ATP to reposition the myosin head after contraction. Here's the myosin head. After the contraction, we need to move it back into its original position. Now, when will we need more myosin to act in interactions? We need more ATP in the situations when we have an increase in the number of myosin to act in interactions, or the rate at which we're creating them. You are going to need more oxygen to make more ATP to reload those myosin heads into the cocked position. This is why myocardial oxygen demand increases in the situations of increased contractility, which means increased force. We need situations of increased force when there's a high blood pressure or high afterload, there's increased formation of them and a high heart rate, or if we have increase in preload. Remember that increased preload means that there's going to be also an increase in wall tension of the ventricular chamber. The law of Laplace defines wall tension. This is an important concept because it also shows up at the pulmonary section when you discuss how surfactant helps prevent alveolar collapse.